Hi and hello. Today's lesson is on triangle congruence part 3. So in this third installment of our lesson on triangle congruence proofs, we will get our last two to bring our sum up to 5 total ways we can prove two triangles are congruent without measuring all of their side lengths and measuring all of their angles. So our lesson question for today is, are two triangles congruent if all 3 pairs of sides are congruent? That's what we're going to try to examine. We want to know if 3 pairs of congruent sides is enough to show two triangles are congruent. So we'll examine the hypotenuse leg and the side-side-side congruence theorems. And then we're also going to apply them to a couple of problems. But before we get into that, I need to warm up and I need to review the perpendicular bisector theorem. So we've got a couple of blanks I need you to fill in. Pause it now, and then we'll come back in just a couple of seconds to wrap up. All right, so the perpendicular bisector theorem says that if the points on the perpendicular bisector of a segment are equidistant from the endpoints. So if C is on the perpendicular bisector, that means it's the same distance from A as it is from B. So if AD is congruent to BD, then CA is the same length as CB. Now this idea also works in reverse. The converse of the Pythagorean perpendicular bisector theorem says that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector. So that's a right angle there at D, and then DA and DB are the same length. All right, so now we can move on to our last two triangle congruence theorems. And we're going to tackle this one, at least to start off with, the same way. I've got two triangles, ABC and DEF, that I don't know everything about. We know some information, but I'm going to try to use rigid transformations, rotation, reflections, and translations to prove that these two triangles are congruent. But first, let's identify what we're given to start with. AB is congruent to DE. We know they're congruent because they each have that one tick mark. Moving down the line, BC is congruent to EF, and then CA is congruent to FD. Right, so that's what we're given as congruent. Now let's use some transformations. First, I want to try to get some points to, at least one point to coincide. So I'm going to translate to move point C to point F, because those are both endpoints of a side that's congruent. While I'm at it, I'm going to go ahead and change the color here, so that way I can still tell them apart later. All right, so now that I've slid point C down to point F, I notice that AC and DF are congruent. So I'm going to rotate it up. So AC maps onto DF. All right, and now the triangles look like reflections. They look like mirrors of each other. So I'm going to reflect over line DF. That way point B coincides with point E. So what we've just shown is that if 3 sides are all we know is congruent about a triangle, then they are going to be the same. This is our side-side-side congruence theorem. If 3 sides of a triangle are congruent to 3 sides of another triangle, then those two triangles are congruent. So here we have triangle ABC is congruent to triangle DEF because of side-side-side. All right, so now that we're back, I'd like to try to apply this to a problem. Rather than proving two triangles are congruent, I want to know what value of x makes these two triangles congruent. So what value of x is going to make triangle PQR congruent to triangle STU? All right, so first let's identify what is already congruent, so that way we know what we need to set equal to. PR is congruent to SU, QR is congruent to TU, which means that PQ has to be equal to TS. So what that lets us do is we can take that 3x plus 4, set it equal to 13, and we'll solve for x. So if I subtract 4 from both sides of the equation, it gives me 3x equals 9. Then I can divide both sides of the equation by 3 and get x equals 3. So if x is 3, then those two triangles are congruent by side, side, side. All right, we got one more proof to go. Triangle congruence by HL. So HL is a special kind of congruence theorem. HL stands for hypotenuse leg. So it's very important to note that only right triangles have a hypotenuse and a leg. So this proof is reserved for right triangles only. Now I would like to be clear, it's not the only one that works for right triangles, just this one only works for right triangles. So let's prove that it works. Let's show that these two triangles here, JKL and XYZ, are congruent even if I only know a hypotenuse and a leg. So the hypotenuse for each one is each marked with 2 tick marks. Hypotenuse is always the longest side of the right triangle, and the legs are marked, one leg is marked congruent. So this is going to work best if we give it some numbers. So let's say a leg is 4 and the hypotenuse for each is 5. I want to know for a fact that these two triangles are congruent. So let's start by solving for our missing side, zy. Luckily, for a right triangle, we know that a squared plus b squared equals c squared. And if I find zy, and it's the same as KL, then these two triangles are congruent by side, side, side. So let's use that Pythagorean theorem, a squared plus b squared equals c squared. So I'll plug 4 in for b, I'll plug 5 in for c, right? The hypotenuse always goes in for c. So a squared plus 16 equals 25. Then I'll move that 16 over. We get a squared equals 9, which tells me that a is equal to 3. So zy is 3 now. I'm not going to repeat all that same work. With KL, I'm going to be doing the exact same math with the exact same numbers, so it's also 3. Therefore, these two triangles are congruent by side, side, side. So hypotenuse leg is really just a shortcut for doing the Pythagorean theorem and then saying that two right triangles are congruent. So we'll abbreviate this to HL. What it says is if the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and a leg of another right triangle, then those two triangles are congruent. So in the above example, triangle JKL is congruent to triangle XYZ just because the hypotenuse and the leg of two right triangles are congruent. So now let's use it. Let's prove that a couple of triangles are congruent using hypotenuse leg. So like I've said, whenever we're asked to prove something, we'll be given some amount of information. In this diagram, we're told that AD is congruent to BC and CD is the perpendicular bisector of AB. So let's start by just marking that stuff true. And we want to prove these two triangles are congruent. So first, AD is congruent to BC. So let's just put a little tick mark on each one. All right, so now this next one gives us a bunch of little pieces we need to take out. CD is the perpendicular bisector of AB. Well, first, because it's perpendicular, that means that that's a right angle right there at M. And then because CD bisects AB, that means AM and AB are the same length. All right, so now let's just examine everything that we know. We're given that pair of congruent sides because it's given. We're given this pair of congruent sides because that's what it means to bisect. And we're given this right angle here in the middle because that's the definition of the word perpendicular. So what we have is two right triangles. And on these right triangles, the legs are congruent and the hypotenuse is congruent. And it's a right triangle. So therefore it has to be congruent by HL. So therefore triangle ADM is congruent to triangle BCM by the hypotenuse leg congruence theorem. All right, so this has been triangle congruence part 3. In all 3 parts, we've learned a total of 5 congruence theorems that we should be able to use. We have 5 triangle congruence proofs. Those are side, 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 angle, side, angle, side, angle, 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 side, and hypotenuse leg. Thank you so much.